Hi everyone, and welcome to Zucal's series on materials. My name is Jaden, and I'll be your online tutor for this course. Overall, this course looks into the scientific principles of why different materials possess different physical and chemical properties, and the role that they play when considering a material for a particular engineering task. In general, we'll be looking at crystalline solids such as metals before moving on to concrete. This course does require a small amount of high school chemistry. If you're not familiar with the idea of different electron shells and the use of the periodic table, I recommend you revise that briefly first. To start off, we'll look at some basic chemistry concepts such as electronegativity and bonding energy to help us explain the different chemical bonds that hold materials together. We'll also look at the different properties different chemical bonds and bonding energies confer. Here is a common model of the atom. Most of the positive charge is contained within the nucleus, and most of the negative charge exists as electrons orbiting the nucleus in layers. The electrons in the outermost shell are the valence electrons. Since the valence electrons are on the outermost shell, they are the most exposed. This makes them most likely to interact with other particles, such as the valence electrons of other atoms. Since the valence electrons are on the outermost shell, they are the most exposed. This makes them most likely to interact with other particles, such as the valence electrons of other atoms and radiation. We will primarily be concerned with the former. Valence electrons are responsible for a number of material properties, such as the type of chemical bonding, the electrical and thermal properties, and optical properties. For this course, we are interested in the type of chemical bonding. For reasons we will discuss later, atoms aim to complete their outer electron shell, or their valence shell. For reasons we will discuss later, atoms aim to complete their outer electron, or valence shells. For reasons we will discuss later, atoms aim to complete their outer electron, or valence shells. This can occur by either filling up their outermost shell, or by emptying it. It is easy to gain or lose one electron, but it subsequently becomes more difficult to lose or gain more electrons. We describe the tendency for atoms to lose or gain electrons as their electronegativity. More formally, electronegativity describes the ability for an atom to receive valence electrons. The electronegativity of an element can be discerned from the periodic table. Atoms to the right have nearly full valence shells and seek to gain electrons to complete their valence shell. The more to the right they are, the less electrons they need to gain, and the more easily they achieve this. In other words, electrons at the right of the periodic table are increasingly electronegative. On the other side of the periodic table are elements with low electronegativity, or electropositive elements. These elements have nearly empty shells and seek to lose electrons to complete their valence shell. The more to the left they are, the less electrons they need to lose. This means electrons to the left of the periodic table are increasingly electropositive. On the far right of the periodic table are elements with full electron shells. These do not need to gain or lose any electrons and are known as noble gases. We stated that atoms want to have complete valence shells, but we haven't discussed why. The reason is that everything wants to achieve its lowest energy state. If you stretch a rubber band, it will try and return to its unstretched state, in other words, its resting state. A ball on a hill will try and roll to the bottom of the hill. In other words, they are both trying to reach their most relaxed configuration. Chemical bonds allow atoms to reach lower energy states by exchanging or sharing electrons. The excess energy is known as the bonding energy. For example, two oxygen atoms have a higher total energy than one oxygen molecule. When the chemical bond is formed, the difference in the total energy is released as the bonding energy. Returning to the rubber band analogy, a rubber band has a length where it is most relaxed. In other words, its most relaxed configuration. Similarly, chemical bonds have a length or an interatomic distance where they are most relaxed. The interatomic distance associated with this relaxed state is the bond length, where the total energy is at a minimum. If we graph the total energy of the bond against the interatomic distance, we find that the bond length occurs when the energy is at a minimum. Returning to the rubber band analogy, a rubber band has a length where it is most relaxed. Similarly, chemical bonds have a length or or an interatomic distance where they are most relaxed. The interatomic distance associated with this relaxed state is the bond length, where the total energy is at a minimum. If we graph the total energy of the bond against the interatomic distance as seen on the right, we find that the bond length occurs where the energy is at a minimum, as you can see on the lowest point of this graph. The depth of this minimum, or the distance between the minimum and the horizontal axis, is the bonding energy. The deeper this minimum is, the greater the bonding energy and the strength of this chemical bond. We can also describe the chemical bond as a force equilibrium. Since atoms have both positive and negative elements, they must experience both attractive and repulsive forces. In a chemical bond, these forces must be in equilibrium and sum up to zero. This is shown on the diagram to the top right, where the total force is graphed against the interatomic distance. The graph intersects with the horizontal axis when the bond is at equilibrium. This is associated with the bond length. Comparing this force distance graph to the previous energy distance graph shows that the force equilibrium is associated with the minimum energy we discussed earlier. We can discern some properties of a chemical bond using these diagrams. For example, we can work out which of these two chemical bonds, A or B, is longer. The bond length is represented by the position of the energy minimum. If this minimum occurs at a small interatomic distance value, the bond is short. Using this logic, since the minimum of A occurs at a shorter distance than the minimum of B, it must be the shorter bond. We can also work out which bond is stronger. This is given by the depth of the minimum. Since the minimum of A is not as deep as the minimum of B, B must have the higher bonding energy and therefore have a stronger bond. Now we'll use the concepts of electronegativity and bonding energy to discuss three types of chemical bonds: ionic, covalent, and metallic. Ionic bonds occur between two atoms with large electronegative differences. In other words, ionic bonds occur between two elements at opposite ends of the periodic table. For example, sodium is an electropositive metal, while chlorine is an electronegative nonmetal. Sodium needs to lose one electron, while chlorine needs to gain one electron. Both atoms can complete their outer shell by transferring an electron. Sodium loses one electron, which is gained by the chlorine atom. Since the sodium atom lost an electron, it gains a net positive charge and becomes a sodium ion. Similarly, the chlorine atom gains a net negative charge and becomes a chloride ion. The resulting ions are now attracted to each other and form an ionic bond. Ionic compounds do not exist as individual molecules. Instead, they exist as ordered continuous structures known as lattices. This is the lowest energy state for all the atoms as a whole. The energy released by forming this lattice is known as the lattice energy, which is a specific type of bonding energy. In order to break this lattice energy must be overcome. Lattice energies are comparatively higher than most bonding energies. Therefore, ionic bonds are quite strong. Since it takes lots of energy to break the lattice, it means that the melting temperature of ionic compounds is high. It also means that the compound is quite stiff, since the bonds do not stretch easily. Ionic compounds are also brittle. As you can see on the right, in the undisturbed state, adjacent ions attract each other. However, when the lattice is dislodged, adjacent ions suddenly repel each other instead, causing the lattice to fall apart. Finally, since electrons are bound to the ions, they do not move freely, and therefore inhibit an electric current, making ionic compounds an insulator. Covalent bonds occur between two electronegative elements that have a small difference in electronegativity. Since both electrons want to gain an electron, they share the electron rather than transferring them using a covalent bond. For example, the carbon in methane shares one electron with each of the 4 hydrogen atoms, therefore gaining the 4 electrons it needs for a complete valence shell. The bonding energy associated with the sharing is quite high. Covalent compounds can exist as individual molecules, such as methane. Each methane molecule itself is held together by a high bonding energy. However, there is very little bonding energy between the molecules themselves. This makes the compound very easy to pull apart and very easy to melt. Covalent compounds can also exist as lattices, such as diamond or silica. These have similar properties to ionic compounds. They have high melting temperatures, are brittle, and are stiff. Metallic bonding occurs between two electropositive elements, where each atom wants to lose electrons. They have a small difference in electronegativity as a result. Metallic bonds occur between two electropositive elements, where each atom wants to lose electrons. Electropositive atoms can achieve this by donating their electrons to a communal pool, or a sea of electrons. The electrons move about freely between the ions and act as a glue that holds the positive ions together. Metallic bonds have low bonding energies, and therefore they have low melting temperatures. Unlike ionic compounds, deformation does not disrupt the attractive forces holding them together. As you can see on the right, the electron glue continues to hold the positive ions together even when the entire compound is deformed. This means metallic compounds are malleable. Since the electrons move freely throughout the compound, they allow an electric current to flow, giving the compound good conductivity. We've discussed how the magnitude of the bonding energy is responsible for the melting temperature of a compound. It is also responsible for the thermal expansion. Initially, the bond length is determined by the minimum energy on the graph. As energy is added to the chemical bond, it begins to oscillate between the two distances present on the graph, marked by the double-sided arrow on the diagram. The average bond length at this new energy is the midpoint of these, marked by the red circle. The more symmetrical the energy distance graph is around the minimum, the less the average bond length changes with energy. This means that the average bond length of A changes less with energy compared to B, since the energy minimum of A is more symmetrical. Therefore, A expands less than B when heated. This means it has a low coefficient of thermal expansion. We can use the bonding force to compare the stiffness of two compounds. If lots of force is experienced when changing the distance a small amount, the compound is stiff. In other words, if the gradient near the force equilibrium is steep, lots of force is generated when changing the bond distance a small amount. Therefore, a steep gradient at the equilibrium represents a stiff compound. Since A has a steeper gradient than B in this case, it is more stiff. In this module, we started by looking at how atoms seek to achieve lower energy states by bonding to each other, using the concepts of electronegativity and bonding energy. We also looked at how atoms with different electronegativities bond to each other using ionic, covalent, and metallic bonds. Finally, we discussed how the bonding energy was responsible for different properties of compounds, such as melting temperatures, coefficient of thermal expansion, and stiffness. For the next few weeks, we'll focus on metals in particular, and the principles that help us describe their physical properties. We'll begin next week by looking at the lattice or crystal structures that metals form. For the next few videos, we'll focus on metals in particular and the principles that help us describe their physical properties. We'll begin next week by looking at the lattice or crystal structures that metals form.